Greetings, my name is Max Laves, I'm a 5th year PhD student, and today I want to talk about uncertainty estimation in medical image denoising with Bayesian deep image prior. Noise in medical imaging affects all modalities, including X-ray, magnetic resonance imaging, CT, ultrasound, or optical coherence tomography, and can obstruct important details for medical diagnosis. Besides traditional approaches for denoising with linear and nonlinear filters, such as the Wiener filter or wavelet denoising, convolutional neural networks have proven to yield superior performance in denoising of natural and medical images recently. The task of denoising is an inverse image problem and aims at reconstructing a clean image x hat from a noisy observation x tilde. Given a noisy image, the denoising can be expressed as optimization problem of the form of this equation. The reconstruction x hat should be close to the noisy image by means of a similarity metric L, but with substantially less noise. The regularizer R here expresses a prior on the reconstructed image, which leads to the reconstruction having less noise than x tilde. As a regularizer, one usually imposes a smoothness constraint by penalizing first or higher order spatial derivatives of the image. More recently, convolutional networks have successfully been used to implicitly learn a regularization prior from a dataset with corrupted and uncorrupted data samples. The CNN extracts important visual features from the noisy input image and reconstructs the input from the extracted features using learned image statistics. This, however, creates the core problem of medical image denoising with deep learning that is addressed in our work. The reconstruction is based on previously learned information, and at worst, the reconstruction can contain false image features that look like valid features but are not actually present in the input image. And due to the excellent denoising performance of CNNs, those false features can be indistinguishable from valid features to a layperson's eye and are embedded in an otherwise visually appealing image. This phenomenon is commonly known as hallucinations and, while may be acceptable in natural images, must be avoided at all costs in medical imaging. Hallucinations can lead to false diagnosis and thus severely compromise patient safety. And to further increase the reliability in the denoised medical images, the reconstruction uncertainty has to be considered. Bayesian neural networks provide the mathematical framework to quantify a per-pixel reconstruction uncertainty. This allows the detection of hallucinations and other artifacts given that the uncertainty is well calibrated. That is, the uncertainty corresponds well with the reconstruction error. And in this work, we employ deep image prior to cope with hallucinations in medical image denoising and provide a new Bayesian approach with Monte Carlo dropout that yields well-calibrated reconstruction uncertainty. We present experimental results on denoising images from X-ray, ultrasound, and OCT, and compared to previous work, our approach leads to better uncertainty estimates and is less prone to overfitting of the noisy image. And besides, our code is publicly available on GitHub. Besides manually engineered priors, convolutional denoising autoencoders have been used to implicitly learn an image prior from data. This can cause hallucinations, as already mentioned, and is therefore very undesirable. However, it was recently shown that the excellent performance of deep networks for inverse image tasks is based not only on their ability to learn image priors from data, but also on the structure of the convolutional image generator itself. An image generator network with randomly initialized parameters is interpreted as a parameterization of an image. The parameters of the network are found by minimizing the pixel-wise squared error with stochastic gradient descent. This is referred to as deep image prior. And during the process of gradient descent, low-frequency image features are reconstructed first, followed by higher frequencies, which makes human supervision necessary to retrieve the optimal denoised image. Therefore, this approach heavily relies on early stopping in order to not overfit the noise. However, a key advantage of deep image prior is the absence of hallucinations, since there's no prior training involved in this approach. A Bayesian approach, however, could alleviate overfitting and additionally provide a reconstruction uncertainty. Bayesian neural networks are able to quantify this reconstruction uncertainty. In the non-Bayesian approach, also called frequentists approach, it is assumed that an optimal point estimate or a theta hat of the parameters of a network exists. The Bayesian approach, on the other hand, assumes that the parameters are also random variables that follow a prior distribution P of theta. This also makes the output y a random variable, and we are now able to reason about the uncertainty of the prediction using the predictive variance of y. If the parameters follow a wide distribution, then y also follows a wide distribution, which we can interpret as high uncertainty. However, to compute the predictive distribution of y, the posterior distribution of the parameters p of theta given a dataset D must be computed. This usually cannot be done analytically, since we must integrate over all possible parameter configurations. And to avoid this problem, we can approximate the posterior distribution using approaches like Monte Carlo dropout. This allows us to estimate the predictive uncertainty, where we usually differentiate between two types of uncertainty. The first one is the aleatoric uncertainty, which results from noise in the data, for example, speckle noise in ultrasound or OCT. It is derived from the conditional log likelihood under the maximum likelihood or maximum posterior framework and can be captured by a deep network directly. To get the aleatoric uncertainty, we assume that the image signal is sampled from a spatial random process and that each pixel I follows a Gaussian distribution with mean x and variance sigma squared. We split the last layer such that our network outputs these values for each pixel. Now, a maximum posterior estimation is performed by minimizing the full negative log likelihood, which leads to the following optimization criterion with added weight decay. And in this case, sigma hat squared captures the pixel-wise aleatoric uncertainty and is jointly estimated with x hat by finding theta that minimizes the log likelihood with gradient descent. Next, we move towards Bayesian view to additionally quantify the epistemic uncertainty, which is caused by the uncertainty in the model parameters. The image generator is extended into a Bayesian neural network under the variational inference framework with Monte Carlo dropout. A prior distribution is placed over the parameters and the network is trained with dropout by minimizing the log likelihood. For inference, t-stochastic forward passes with dropout are performed to sample from the approximate Bayesian posterior. We use Monte Carlo integration to estimate the predictive mean and the predictive variance. The resulting mean is used as an estimation of the noise-free image, and sigma hat squared in this case is used as an uncertainty map. We use the mean over the pixel coordinates additionally as a scalar uncertainty value. But how do we know if we can trust the estimated uncertainty? We want the uncertainty to be well calibrated. And following recent literature, we define predictive uncertainty to be well calibrated if it correlates linearly with the predictive error. That is, if all pixels in a batch were estimated with uncertainty of 0.2, we would expect that the predictive error also equals 0.2. This equation here, however, cannot be computed with finite data. And we therefore approximate this with the expected uncertainty calibration error for regression, or UCE for short. The uncertainty output of a deep model is partitioned into m bins with equal width, and a weighted average of the differences between predictive error and uncertainty is used. That means that the discrepancy between the error and the uncertainty is weighted by the number of pixels per bin. And additionally, we plot the error versus the uncertainty to create such calibration diagrams. We refer to our presented approach as Monte Carlo deep image prior, and evaluate its denoising performance and the calibration of uncertainty on 3 different medical imaging modalities using images from public datasets. First, we create a ground truth noise-reduced image, which we use to compute denoising performance metrics by smoothing and downsampling the original image. Downsampling involves averaging over highly correlated neighboring pixels affected by uncorrelated noise. And this decreases the observation noise by sacrificing image resolution. Next, we simulate noise patterns. Speckle noise in ultrasound and OCT can be modeled by additive Gaussian white noise, and noise in low-dose X-ray originates from uneven photon density and can be modeled with Poisson noise. However, under some assumptions, this noise pattern can also be modeled by Gaussian noise. We then use our presented approach to denoise the created images and evaluate the results using the peak signal to noise ratio and the mentioned uncertainty calibration error. We compare our results to standard deep image prior, so the non-Bayesian deep image prior, and to another recent Bayesian approach to deep image prior, which uses stochastic gradient Langevin dynamics, which only considers the epistemic uncertainty. Therefore, we train the SGLD approach to additionally consider aleatoric uncertainty and denote this by SGLD plus NLL. The authors of this approach claim that their Bayesian approach alleviates the need for manual early stopping. Next, the results are presented threefold. First, we show the denoising performance by providing the denoised images and PSNR values after convergence. Second, we show possible overfitting by plotting the PSNR values between the reconstruction and the ground truth image during the optimization. And third, we show goodness of uncertainty by providing calibration diagrams and uncertainty maps. Our experiments confirm what was already known. The non-Bayesian deep image prior quickly overfits the noisy image here on the left. However, the SGLD approach shows almost identical overfitting behavior in our experiments, which is in contrast to what is stated by Chen et al., even when using the code provided by the authors. Now, let's have a look at the PSNR values. The narrow peaks here during optimization show that manually performed early stopping is essential to obtain a reconstructed image with less noise. And in this case, the PSNR between the reconstruction and the ground truth approaches the value of the PSNR between the noisy image and the ground truth, thus reconstructing the noise as well. The SGLD with aleatoric uncertainty, the green line in this plot shows slightly less overfitting of the noisy image. Our approach, however, which is denoted by the red line, does not show a sharp peak and safely converges to its highest PSNR value. This requires no manual early stopping in order to obtain a good denoised image. And the plots for the other images look very similar and show that we did not cherry-pick the test image here. Although it was not the intention of this work to reach highest possible PSNR values, we even outperform the other methods with early stopping applied on the OCT and X-ray image. Note that we did not perform early stopping for our approach. Now let's have a look at the calibration of the uncertainty. Due to overfitting the noisy image without early stopping, the reconstruction error from SGLD concentrates around 0.0 compared to the noisy image, which results in low UCE values. On the ultrasound and OCT image, the uncertainty from SGLD collapses to a single bin in the calibration diagram and does not allow to reason whether the reconstructed image is valid or not. The uncertainty map plots the pixel-wise uncertainty and is plain black in this case due to the overfitting. Therefore, we compare our results to the results from SGLD with early stopping applied. Again, we did not perform early stopping in our approach. Now, SGLD also yields well-calibrated uncertainty and allows to detect errors and artifacts in the reconstructed image as well. It is worth pointing out that in both cases, the mean uncertainty U is very close to the noise level of 0.1 of the standard deviation of the additive Gaussian white noise. And with this, I want to conclude my talk. In this work, we provided a new Bayesian approach to deep image prior. We applied this to medical image denoising of 3 different modalities and provide state-of-the-art performance in denoising with deep image prior. Our Bayesian treatment does not need carefully applied early stopping and yields well-calibrated uncertainty. The deep image prior framework is especially interesting in medical imaging as it does not require supervised training and thus does not suffer from hallucinations. The presented approach can further be applied to deformable registration or other inverse image tasks in the medical domain. Thank you very much for your attention and goodbye.